Today I'm going to solve the first practice problem for homework number 3, which involves an oven. So to restate the problem definition, we have, and I'm actually going to start with the picture today, because that helps us understand what's going on. We've got an oven wall, and inside this oven we have, you guessed it, some hot gases at T infinity with a convection coefficient against the inside wall of H. Then the inside wall of the oven, we're going to call TSI for a minute. We're going to give numerical values to these soon. Then the outside surface of the oven, we will call TS0. All right, now this oven has 3 different parts of the wall, each with a slightly different thermal conductivity. So we will call those Ka, Kb, and Kc. Likewise, they have different thicknesses or lengths, whatever you prefer to say there. In this case, La, Lb, and Lc. Okay, we are given the values for thermal conductivity and length. In this case, wall A has a thermal conductivity of 25 and a length of 0.4 meters. Wall B has a length of 0.2 meters and an unknown thermal conductivity. Then wall C has a thermal conductivity of 60 watts per meter Kelvin, and it has a length of 0.2 meters. Okay, likewise, our temperatures. The temperature of the inside wall has been measured to be 600 degrees Celsius. Likewise, the temperature of the outside wall was measured to be 20 degrees Celsius. Finally, the hot gases inside of the oven are at 800 degrees C, and the convection coefficient between the air and the wall is 25 watts per meter squared Kelvin. Okay, so we've got all of this, and we are asked to find K. What is Kb? Okay, so we're going to draw our energy balance / control volume. Now, our approach on this is going to be a thermal circuit. And with thermal circuits, it's hard to draw an energy balance that makes sense because it changes as we do the circuit. So for this case, I'm going to draw 2. I'm going to draw that circuit, or our entire wall, control volume. And then I'm also going to draw a control surface right there. Okay, so there's our energy balance. All right, let's talk about our approach. For this approach, we're going to use a thermal circuit. The reason we're going to use a thermal circuit is because we have 1D conduction, which is one of our stipulations for that. This is only conduction in one dimension. Likewise, we are at steady state. And so with those two things, we are left with a 1D steady state problem, and we can use a thermal circuit. And we're going to use that thermal circuit on the wall, and we're going to use it on the left surface. Okay, so let's actually build our thermal circuit. We're going to do that down here. So first, we draw our nodes, where our first node is T infinity. We draw our resistor. So there's our first node corresponding to this. We draw a resistor representing convection at this wall, and then the temperature of that wall is our next node, or TSI. Then we have conduction from here to there, and here to there. So I'm not actually going to name the temperatures of these walls because, as you will see, we don't need to know that information. But I am going to draw them. So here's the temperature of that wall interface, the temperature at that wall interface, and finally, the temperature of our outer wall, or TSO. Okay, so now we need to model what's going to happen. I'm going to use heat flux in this problem. So we have a constant heat flux moving through our 1D wall, and in all of these cases, we have resistance. So first we say there is a resistance accounting for convection at this surface. And then we have conduction resistance moving through all three of these walls. So this is R for conduction A. So that's the resistance of the conduction through this wall. This is the resistance of the conduction through wall B, and the resistance of conduction through wall C. Okay, so now we need to model what all of those are. Again, we're using our flux resistances. So for convection, that just becomes 1 over H, very simple. Okay, now we have 3 conduction resistances. Okay, and those, you will remember, let's just draw that here, are equal to L over K, or the length of our wall divided by the thermal conductivity of that wall. So for wall A, that's just LA over KA. For wall B, that's LB over KB. And for C, you guessed it, that is LC over KC. All right, so we have our resistances, we have our thermal circuit. Now what we're going to do is we're going to choose portions of this circuit in order to find Q double prime, and then use that Q double prime in order to solve for what KB is here in our conduction B. Okay, so we are trying to find, again, what this value is, a thermal conductivity, KB. In order to do that, we're going to look at the thermal circuit in 2 ways. First, we need to find what our heat flux is. You'll remember, for a circuit, the heat flux is equal to the temperature difference between the nodes we look at divided by the total added resistances between those 2 nodes. So to find the heat flux, we're going to look from TSI to TSO. The reason we are doing that is because we know what TSI and TSO is. That means we will know delta T. Likewise, well, we don't know this yet, and we don't know this yet. But once we find this using a different circuit, we'll be able to plug it in. So let's put that all together. So this is Q double prime is equal to our delta T between our 2 points. So that's TSI minus TSO. And now we need to find R double prime total, or the sum of the resistances between those 2 points. So that's just adding up our conduction A, our conduction B, and our conduction C. So that looks like this. Okay, so now you see we don't know Q double prime yet, and we don't know KB. So what we're going to need to do is find a different circuit that allows us to figure out what Q double prime is. Well, what could we do? We have this little circuit here between T infinity and TSI. The reason we're going to do that is we know T infinity, we know TSI, and we can find what R double prime convection is since we know what H is. So writing out that circuit, Q double prime equals T infinity minus TSI divided by our resistance, which in this case is just 1 over H. Okay, so plugging in those values, T infinity is 800, TSI is 600, and 1 over H, which is 25. So when we evaluate that expression, we get a Q double prime of 5,000 watts per meter squared. So now we used this little circuit to find Q double prime, and now with that we can plug our value into there. This is now known, and we can solve for our only unknown, the thing we want to know, KB. So plugging everything in, we have 5,000 equals TSI minus TSO, so 600 minus 20, and those are both in degree C. And now we plug in values for all of our resistances. So there's LA over KA plus LB, which is 0.2 meters, over our unknown, KB. And then we have LC, which is 0.2 meters, divided by KC, which is 60 watts per meters Kelvin. All right, so one unknown, all we have to do is simplify this expression, which I'm not going to do for you here on the board. After we simplify that, then you'll find that KB is equal to 2.07 watts per meter Kelvin. Okay, so again, the takeaway here is we used this thermal circuit in two different ways. First, we used this little circuit to find Q double prime because we knew everything else. Then with Q double prime, we could use this big circuit in order to find R double prime conduction B. Now, if we wanted to, we could have found inside temperatures, but we didn't need to in this case. Okay, that's our problem. Thanks for watching.